astro-interferometry, in a nutshell, involves using multiple telescopes spread far apart and complex calculations to simulate a lens as large as the distance between them. Imaging the black hole's shadow located in the core of the galaxy Messier 87 was done with a virtual lens the size of Earth's diameter. But you know what? We can do better than this. Way better with today's technology. We just have to think bigger. Last week, we discussed using warp speed to deploy an array of telescopes as wide as a star system, allowing Starfleet to peer into the recent past. With warp speed, deployment could take just minutes. In the real world, we don't have warp speed, but there's a way to create a telescope array as wide as Earth's orbit in only a year. Such an array would make the James Webb Space Telescope seem nearsighted. I'd love to hear a real astrophysicist discuss the logistics, as well as applications I haven't even contemplated. The idea is feasible, though the funding, which might not be as expensive as a manned moonshot or especially a manned Mars shot, could be beyond our reach with our current small tax base. And a smaller NASA neutered by budget cuts, billionaires and corporations thinking and acting small.
We have not left low Earth orbit in 50 years.
Well, how come we could do this 50 years ago? They just delayed Artemis again till 2025. How come we used to be able to send rockets up there and we can't anymore? What is happening?
By deploying a ring of self-contained space telescopes as Earth orbits the Sun, we could cover Earth's orbit in a year, 186 million miles, approximately 300 million kilometers across. We deposit around 36 cameras every 10 degrees along Earth's orbit. Once we synthesize all the readings, we'll essentially be looking through the largest camera ever created. This array could allow us not just to detect alien planets within 100 light years, but to see them, their coastlines, their moons, and more. The array would resolve features as small as 66.8 meters, about 219 feet, on Proxima Centauri, enabling us to discern major surface structures like large buildings or geological formations. For stars and planets up to 100 light years away, it could resolve features down to 1.58 kilometers, 0.98 miles, sufficient to study major planetary features like continents and mountain ranges. But wait, there's more. If we had a separate mission to Mars or Jupiter, we could make this array expandable. Adding a single eye at Jupiter improves our resolution for Proxima Centauri, which is 4 light years away, to 18.6 meters, 61 feet, enough to study large structures or signs of artificial construction. Even without building the complete Earth ring, we could make all future probes interconnected, slowly constructing the largest eye possible. The resolution would improve in specific directions as more eyes are added. For example, without the stray camera at Jupiter, the Earth-based ring could resolve structures down to 40 kilometers in Andromeda. That's a whole separate galaxy. Adding the Jupiter outlier improves this to 11 kilometers, demonstrating how a single addition at such a vast distance dramatically enhances resolution. With a full Neptune ring, achievable with current technology, albeit with patience, we could even resolve volcanoes on planets in Andromeda. And speaking of galaxies, the Triangulum galaxy is 500,000 light years farther away. Unlike Andromeda, it won't collide with the Milky Way in 5 billion years. With an Earth ring, we could resolve planetary features in Triangulum down to the mountain range level. Throw in 2 stray eyes orbiting Mars and Jupiter, and our resolution increases by 3,600%, enabling us to map cities on planets in Triangulum without ever visiting them. Within 100 light years, our stellar neighborhood contains approximately 515 stars, encompassing a range of types. While stellar mass black holes are rarer, a few likely exist within this radius. With this array, we could eventually locate and study them up close. As the Earth ring continues to be upgraded by new missions, we could potentially observe large-scale alien life, like forests or lakes, rather than merely detecting signs of it. So why not? This doesn't require new technology. It requires cooperation, design, and tax dollars. We can do this, and I'd love to hear professional astrophysicists discuss the idea. Now, for the sci-fi twist. What could Starfleet achieve with warp speed starships? Despite their ability to traverse the alpha and beta quadrants using wormholes, they are limited to one sector of the galaxy. They can't reach other galaxies or even the far side of the Milky Way. This limitation highlights that there's still much to explore by studying the sky. Well, with warp speed, they could construct a 4-light-year ring between star systems. With such a ring, Starfleet could resolve life in other galaxies. In Andromeda, they'd achieve a resolution of 82 feet, 25 meters. Using subspace communication and warp speed, they wouldn't be limited to a mere 4-light-year ring. They could create a 100-light-year ring that would enable resolution down to 1 meter in Andromeda, and for close galaxies like Triangulum, resolution at the centimeter scale. Starfleet could observe life on distant planets at an individual level. It would have extreme flexibility. Unlike fixed-position satellites, warp-capable shuttles could dynamically adjust their configurations based on the target of observation. Need to study Andromeda? Reposition shuttles for maximum resolution in that direction. Want parallax interferometry of a polar region? Shift the array for optimal orientation. What's more, long-range sensors that work faster than light would provide a fresher view of the universe. Andromeda, for example, could be studied as it appeared 2 billion years ago, with electromagnetic waves versus 2,700 years ago, using subspace long-range sensors. Such sensors could reveal active civilizations in distant galaxies, some of which might even be looking at us. And if you want to go for insane resolution, we could probably see faces in other galaxies. They could set up part of a ring in the alpha quadrant and the other in the beta quadrant on the other side of the wormhole. If I were in Starfleet, I'd push hard for this. For now, though, I'd settle for seeing NASA return to its former glory. If this idea were proposed to the old NASA, I think they might seriously consider it, even at a smaller scale. At the very least, we should establish protocols for all future probes to include omnidirectional cameras and the ability to coordinate with other probes across the solar system, even if we can't yet form a complete double parallax Earth ring. This is achievable. Devices with multiple cameras pointing north and south could run thousands of automatic exposures, while simultaneously receiving auxiliary experiments, even near the galactic plane, where interferometry is limited. This array would surpass anything currently Earth-based. If we deployed twin satellites and created 2 rings, we could achieve advanced interferometry for the galactic plane too, while also enabling parallax interferometry for the polar skies. Deployment could occur in pairs, with one satellite heading 1 million miles south, completing 2 rings in 1 year. This setup would create a 300 million kilometer parallax lens and an excellent interferometer for observing the galactic plane from all directions. Sure, there would be drift, and Earth's gravity would disrupt the ring as it passed. Cameras would need to adjust, and satellites replaced over decades as necessary. However, software could compensate for drift, and we could integrate any future probes into the ring for additional capacity. With this setup, we'd achieve unparalleled discoveries. It wouldn't require 36 launches. We could deploy in stages, letting satellites self-deploy after launch. I'd love feedback from an actual astrophysicist on this idea. I'll be forwarding this to NASA, assuming DOGE hasn't shut down their internet yet. Thanks for watching, and don't forget to like and subscribe. Next week, we will take short looks at various superheroes and how they would tick in the real world.